Welcome to Earth Science, everybody. So, let's talk about the greenhouse effect, which I don't think is technically going to be a whole lot of new stuff here. I think you're going to, if you've been really tuned into the notes and the work we've done, you're going to be okay here. Why do cars get so hot when sitting in the sun? So, we have Mr. Nyland's El Camino here. Why, if that is sitting in a parking lot on a sunny day, does it get so hot inside the car? Like hotter than it is outside, right? So, I mean, think about that for a minute. Why is that? You can say, well, okay, the sunlight's hitting it. But what if the sunlight hits it and like hits something shiny and then reflects? Like, what is it that allows sunlight in through the glass, allows energy in through the glass, but doesn't let the energy back out? That's where the key difference is. And it goes back to those absorption and radiation experiments that we've been working on. So I'd like you to try this in the notes. This is hard in a normal year with a pen. It's going to be a little harder this year. But I'm going to draw a wavelength of energy, and we'll just call this sunlight, visible light. Yes, I'd like you to be doing these notes. So press pause and go open it up if you need to. Now, sunlight can go right through the windows, as you know, right? That's not a big, amazing or science fact. Sunlight goes through windows. So it goes through the windows, it hits the inside of the car. And when it hits something in there that can absorb energy, like the beaker of sand absorbed energy, that thing heats up. So I'm going to draw it coming right in through the back window there, right down and hitting Mr. Nyland's seats or whatever may be in there. Okay. As a result, the temperature of the car goes up. But still, I mean, so that's not the end of the problem because the sunlight's hitting the outside of the car too. It's hitting the parking lot and all of that too. Why does it get hotter inside? Now, the thing is that we got to keep in mind is this whole process of radiation. So that's why I wanted to really like very slowly and deliberately think about those two separate steps in that experiment we did. We heated up something for 15 minutes and then we let it cool off for 15 minutes, but really that's radiation. That's it giving its energy back to the room. Now, something that's warm gives off energy. I'll try to do a video at some point of, I have an infrared camera. I really don't know how I would do it. I have to point the laptop on it, but I have an infrared camera. Everything that's warm, and if there's people in the room here and I pointed at them, you'll see them like glowing because it's picking up infrared energy. The warmer something is, the more infrared energy it gives off. Now, it's like that lab, I said this is a two-step thing. It absorbs for 15 minutes and it cools for 15 minutes. Really, as it's absorbing, it's also going to be giving off more and more and more infrared energy. If we watch that with a little camera, which we do in a normal year, you'd see it like glowing brighter and brighter and brighter because as it gets warmer, it's also giving off more infrared energy. And it's a huge difference because the sunlight right down here on this electromagnetic spectrum thing that I'll explain to you in a minute comes into the visible spectrum, and there's ultraviolet rays with that too. I mean, that's why we wear sunblock and sunglasses, like have UV protection, right? But when something gets hot, it gives off infrared, which has a longer wavelength. So I'll circle that in green. Like the greens are going to be the key here. The reds are what we say came in, right? Should have done the arrow in red too, but hey, we can do it. We got time, right? We're not in a hurry. All right, so the sunlight's coming in at that visible to ultraviolet end of the spectrum, section of the spectrum. But when something cools off, or when it just gets warmer and starts giving off more energy, it gives it off at a longer wavelength. And the key is that that longer wavelength does not make it through glass. So longer wavelength. I don't know if I can change the colors here. Nah, you can't change the colors on one word. I'll do it in capitals because there's the key. Longer wavelength infrared energy is trapped by glass. If it didn't, this wouldn't happen. The energy would go through the window and come back out through the window, and the temperature inside the car would be the same. Everybody that's gotten into a hot car, like on a hot day that's been sitting in the parking lot, knows that it gets hot in there. And this is the reason why that infrared energy cannot get back out through the glass. The inside gets hotter, gives off more infrared, it can't get out. So there's the like physics behind a greenhouse too. If you have a greenhouse or one of those like hoop houses made out of plastic, so you can get seeds going early in spring, things like that. Um, that's the thing. So what you want inside of there is some sort of like if you have a greenhouse, you want to put something that's good at absorbing energy in there. Like people get just Home Depot buckets and paint them black because black is going to absorb the energy better. Fill them with water because water holds on to energy really well. Or you can get brick that's pretty good at it. That way, that brick or that water acts as what we call a thermal mass. It holds on to that energy, like the seats in a car, so that maybe throughout the night it can send that infrared out more slowly and get trapped by the glass all night. So there's that's it's called the greenhouse effect. That's what this is because that's how greenhouses work, right? In fact, that's what this. Where's your holy greenhouse effect? All right. So this electromagnetic spectrum. There's a simpler version in your reference tables. I don't think I have one right here, but I can always pause. New York State changes these things around every 5, 10 years. So if you look at your reference tables, you're going to see a version that looks like that. It's a lot simpler. The good news for you, if you don't want to get stumped on these questions, is that they no longer ask questions about the specific wavelengths. If you see all these numbers, that's how long it is from the crest of one wave to the crest of the next wave. Okay. Now I'm saying that because today I am going to ask you one right down here. 72, state a possible wavelength of infrared energy. Just look right there and give me one of those numbers. It's like it's not that hard, but you don't have to do that anymore because it's now this. But hey, what the heck? We can spend a couple years ago and try one of those questions. So this is like all of the wavelengths of energy that might affect us. Going from like bad news down here. We don't want to be hanging around gamma rays at all. X-rays very little, and ultraviolet really not a whole lot either. Um, Visible light, which then you break down and you might recognize these as the colors of the rainbow, Roy G. Biv, to that infrared to microwaves to radio waves, going from the decreasing end to the increasing end. The questions on that, again, you'll practice a little bit down below. Won't be too terrible. So the big trick, the big moral of the story today is to recognize that our Earth and atmosphere really do the same thing as a car in a parking lot. The sun's energy comes out at a shorter wavelength, hits the Earth, which heats up. Then the Earth is warm, which means it's giving off more infrared energy. And that infrared energy that escapes gets trapped by greenhouse gases. Okay? I put this on here sideways. This is like the layers of the atmosphere. You saw this in the density of liquids lab very briefly. Here it is again very briefly. We'll really get into the meat and potatoes on this thing when we get to meteorology. But the layers of the atmosphere, the lowest where we live is the troposphere. Then as you go up, you go into the stratosphere, mesosphere, and thermosphere. I think that's down below too, which is why I threw it on there. But our atmosphere contains these greenhouse gases. Now, this is a good thing. What would happen if there's no greenhouse effect? Well, let's pretend that either the infrared just made it out through the greenhouse gases without any problem, or if this like transition wasn't a thing. Because like this, if it reflects right here, if it just bounces off of like something white, like a sheet of ice or Antarctica or the tops of clouds, it just goes right back out. Because if it can come in easily, it can go back out easily. So this is not a matter of reflection; it's a matter of absorption and radiation. There's no greenhouse effect though, and we did mention this on the lab. The temp of the Earth would plummet. I mean, drop significantly at night. Like on the moon at night, it goes down like hundreds of degrees. So there would be no stability. I mean, it'd be much hotter during the day and much colder at nights. And chances are, the way that we came to be evolutionarily, we wouldn't exist. We really depend on this greenhouse effect. So it's a good thing, absolutely. Without it, life as we know it wouldn't exist. The conditions on the planet as we know that wouldn't exist. Is it a bad thing? Well, this process is dependent on greenhouse gases. No, where it might be a bad thing, or in reality is becoming a bad thing is if there are too many greenhouse gases, the this effect gets more and more and more efficient at trapping heats. That's just mathematical. Now, there's a lot of people that are going to try to talk you out of the idea of climate change for mainly for political reasons or misinformed. Maybe they were miseducated at some point. This is simple like physics and arithmetic. This happens. So the more of a efficient atmosphere we have at holding on to this energy, the warmer it's going to be. And you make that more efficient by adding too much carbon dioxide and methane. Now, when I say efficient, you usually say, oh, efficient, that's good. But I'm saying, okay, it doesn't want to give me another text back for some reason. And methane. I'm saying efficient maybe in a negative context. If it's more efficiently holding onto heat, it's going to keep us warmer. And then more energy from the sun comes, and that keeps us warmer, and that keeps us warmer, and that keeps us warmer. With the result being a shifting climate towards the warm, which is going to have shifting effects. And that's going to be where people maybe have some different ideas and some discussion points to make. But this is something that is not really disputable. This is like if we had a little bit fancier equipment here in the lab, we could demonstrate this very easily. Okay. All right. This is a set of Regents questions I'm going to have you check out. Please, yes, do read this stuff. But then the questions won't be too bad. I helped you out with that one already. Lowest layer of the atmosphere, that's up there. Why would sea levels rise if it gets warmer? Think about that. Let me just say one thing about 74 here. State one possible change humans can make to significantly reduce the amount of greenhouse gases added to the atmosphere each year. There's always a question like this on the Regents. It'll either be something about like this, like something in an environmental realm, or something in a once we study earthquakes and volcanoes, something you can do to be prepared for earthquakes, volcanoes, storms. The key, if you want the points on the Regents, if there is a Regents, the key is to keep it simple. Don't try to be too overly creative. I've had people say things like dumping concrete into fault lines to seal them up, and that's just like that's not going to work. So don't try to get too outrageous here. If these are the things that are causing the problems, use your head and tell me how we could help ourselves out. All right, that'll do it for those notes. Look for the next part in the survival guide. Thanks for sticking with me.